In this lecture, we'll be learning about ARP, or autoregressive of order P processes and their estimation. Recall the definition for our autoregressive 1 process, or AR1 process. We have a white noise process, epsilon 1, epsilon 2, epsilon 3, so forth. And we say that the sequence y1, y2, y3, so on and so forth is an AR1 process if for some constant parameters mu and phi, we have the following expression for all t. And remember, the way that we think of this is, if you think of t on a daily time scale, which of course you don't have to, this can work on any time scale, but it's often most intuitive to think on a daily time scale, how the value of yt differs from its mean mu today equals some random term coming from the white noise representing new information, the effect of new information, plus some piece, think of phi typically as a percentage, some percentage of how y differed from its mean yesterday. So this builds in, we call phi the memory parameter, because the way y differs from its mean today remembers some of how it differed from its mean yesterday. And we had the condition that this process yt is stationary if phi in absolute value is less than 1. We now take this idea and extend to memory going beyond just one time period, or one day, in the example we're talking about, when we introduce the idea of an ARP process. So we have the same kind of setup. You have some white noise process, your epsilons, and we say your y sub i's are an ARP process if now you have p memory parameters, specifically because you are remembering something from 1 to up to p previous time periods. And we can think of this in the same kind of way, that yt today differs from its mean with some effect of new information that's coming from your white noise term for time t. And then you have a piece of memory for each of the p previous time periods. So it's a natural extension of the AR1 process. And of course, if p equals 1, this is exactly the definition of the AR1. Typically now, we reorganize things a bit so that we can rewrite our expression in this way. Essentially, we take each of these terms, so here you'd have phi p times mu. Here you have phi 2 times mu. Here you have phi 1 times mu. And then you bring this mu to the other side of the equation. And the result, when you combine all of these, is you have mu times 1. Notice that these mu's have negative signs associated with them. So 1 minus phi 1 minus phi 2 minus so on and so forth to phi p. And we are able to, if we call this thing, by definition, beta naught, because it's a constant, notice that there's no y's appearing here, then we can rewrite this equation, equation 2, as equation 3. So we have this term here, this beta 0, and then you still have the phi 1 yt minus 1, phi 2 yt minus 2, phi p yt minus p, and the epsilon t. And we write it this way because now we can think of this as a regression. And this is a regression where the dependent variable is your yt, and your predictor variables are the earlier versions of y. Hence, why we call this an autoregressive process of order p. So you are regressing based on the earlier values of your y process. So this is how we define and think of an ARP process. And again, it helps to think of intuitively these fees as a percentage. What's the percentage of memory of yesterday's deviation from the mean? What's the percentage of memory for 2 days ago, the deviation from the mean? The stationarity properties requirement is a bit more complicated than in the AR1 process, and we won't get into it here. But again, roughly speaking, you want to think of these phi sub i's as percentages, typically percentages in terms of between 0 and 1. That's the natural intuitive way to think of this. So if phi 1 was 0.5, you'd be remembering 50% of yesterday's deviation from the mean. If phi 2 was 0.25, you'd be remembering 25% of the deviation from the mean from 2 days ago, so on and so forth. Now that we have this definition of a process, an ARP process, what do we do if you want to actually sync this up to data? So suppose you have a time series, so real data, y1 up to yn, and you have your ARP model as we just wrote it. We now need to estimate the mu, the mean of the process, and the memory parameters phi 1 through phi p. And notice that then gives you an estimate for beta naught, because recall, if we go back, your beta naught depends on the phis and the mu. And we take a least squares approach. So we define the function f of mu phi 1 up to phi p in the following way. So we're taking our actual data points, and if you think of this equation here, notice you have yt on the left, that's yt, that's our data point for time t, and then on the right we have the value according to the ARP definition without the noise term. Put another way, if you subtract the right-hand side of this expression from both sides, you see that this expression inside the square is nothing more than epsilon t. So we're taking the sum of the squares of the errors, of the white noise terms. And our goal is to minimize this function f. Since it's a least squares problem, it turns out that f is a convex function, which means the first order conditions for a minimizer are both necessary and sufficient. So for a global minimizer. So what that means is your first order condition of taking the gradient of f and setting it equal to 0, if you can solve this, then the resulting solution for mu phi 1 up through phi p gives you a global minimizer of this least squares function. And recall what this means. This is essentially a condition from optimization. You can think of it in calculus. You're checking that the tangent hyperplane is horizontal. And because the function is convex, So if you have something like a paraboloid, and then your tangent hyperplane, of course I'm drawing this in 3D because we can't picture it higher, your tangent hyperplane at this point being horizontal identifies that point as your minimizer. So for instance, this could be, if we were doing an AR1, this here could be the mu axis, and this could be the phi1 axis. And again, it's the same principle, just in higher dimensions. We can't picture it nicely like this. So in order to fit this to data, we use typically some numerical routine to solve this system here, the gradient of this f being equal to 0. When you do that, you then have estimators for mu, phi1, phi2, up to phi p, and also beta naught, because that's derived from these previous estimators. Now that we have those estimators, we can then look at what we call the residuals. So take your white noise. This is what it is theoretically. So remember, this is when you just take the ARP defining equation and solve for epsilon t. When we replace these terms, the parameters, with their estimator partners, so beta naught, replace it with beta naught hat, phi I, replace with phi I hat, what you now have are realized values of the epsilon t's as a result of the minimization of the least squares function, which we call residuals. And now we come back to the question of, was it an appropriate model? Was the ARP an appropriate model to fit to this time series data? Well, the reasoning behind how we check that is that if this is a good model, if it's an appropriate model, the realized epsilon t's, those residuals, should look like the theoretical white noise process that we postulated for these epsilon t's. So we then form these residuals and test them against the theoretical white noise process. Do you believe that they actually come from your white noise process? So for example, if you had assumed Gaussian white noise, you can do a statistical test to check and see if these actual residuals are consistent with that Gaussian white noise process. If they are, that is evidence in support of this being a good model. Or I should say an appropriate model for your given data. So to sum up, the idea behind the ARP process really is the natural extension of the AR1. AR1 says how you differ from today's mean. That remembers a piece of how you differed from the mean yesterday, and here we just allow for that same mechanism, but with p days in the past.